So as some of you may know, this is our second event in a series of events that we intend to host on topics related to artificial intelligence. So for today's event, we have two really good speakers. We have Carlos and Juan with us today. So they will be giving a presentation each, and then we'll have our own time to ask them questions at the end. So for this, just a reminder to make sure that if you have any questions or you want to ask them any questions, make sure you use the Q&A section of the Zoom, so not the chat section, which should be disabled. Okay, so with that, I am going to pass it off to Paula. She has a couple words, and then we'll go ahead and get started.
Great, thanks so much, Nes, for the introduction. So I just wanted to give a little bit of context to what we are doing here today, and in which way we are gathering. So this series of events is part of the Rafael del Pino Club of Scientists that was born in the Rafael del Pino Alumni Club, where some scholars that we had some scientific background, we gathered together and we realized that we shared some common principles and values. And it is held open, so most of you joining are not Rafael del Pino scholars, because we also realized that we also had people around that share those principles and values. So we wanted to make this community not unique to the scholars, but rather to those of us, regardless of the label, that have a similar way of looking at science and that have common interests both inside and outside the lab. So our aim in the Rafael del Pino Club of Scientists, that has the support of the Rafael del Pino Foundation, is to promote the technological innovation as a pivotal value in economy, especially in Spain. And our approach is bottom up. So we want to generate a community of scientists from different areas and around different topics. So today we are holding this second event, as Ines mentioned, around artificial intelligence and predictive modeling. So both Ines and Manuel have been working relentlessly on this series that we think is very important and very interesting, because there are not many communities of young Spanish scientists working around these topics. And you might be surprised for us holding this in English, and it is actually because we want to make the most in terms of getting and knowing more ideas. But one of the goals is to actually gather together all the Spanish scientists who are in a daily basis working in this field, so we can get to know each other, get to know other like-minded scientists, perhaps a little bit farther in their scientific career, and to be able to follow their example. So I guess without further ado, because we are here to listen both to Carlos and to Juan, I give the floor back to Ines, and I encourage you to join our mailing lists and to remain connected to this community. So thanks so much.
Awesome. Thank you, Paula. So let's go ahead and Carlos, whenever you're ready, feel free to share your slides and we'll dive into his presentation. I can see your slides, Carlos, whenever you want to start, go ahead.
You're muted, Carlos.
Is it working now?
Yep.
Okay, perfect. So first, thank you so much for inviting me here today. I'm very happy to come and share some of my thoughts on machine learning. My name is Carlos, and I'm a researcher at Google Brain, which is one of the research labs or research teams at Google. So my talk is going to be basically a mix of different things. So there's no super clear common theme. First, I'll talk a bit about my path in machine learning. I think there's a lot of students in the audience. So first, I'll describe what I did, and at the end, I also have some brief, one slide with some tips for students that are interested in machine learning. So most of the talk is going to be focused on my vision of where machine learning is right now, where it's been in the last few years, and some potential or trends for the next few years. So, okay, so my path in machine learning, I'm from Spain, I'm from Madrid. I did my undergrad in Universidad Autónoma, math and computer science in 2006, which is, a few years ago. At the time when I started, I didn't know, I knew I like math, I like computer science, didn't know how that could be useful. I had some intuition that it was probably going to be useful in some way, but it was not until I did my Erasmus or actually my master's in the UK when I realized kind of how powerful both disciplines were, especially together. But at the very beginning, I was maybe a bit more interested in math, so I focused on combinatorics, graph theory, which is, I guess, a subset of discrete mathematics, very theoretical, like proving theorems and so on. And I actually enjoyed it a bit, but I knew I probably didn't want to stay in academia, and for that kind of work, academia is probably the main way to go, I would say. So but I wanted to keep studying, so I went to the US to do a PhD without a very clear clue on what kind of PhD I wanted to do. Definitely technical, math, computer science, the intersection. And there is where I really got to see machine learning, data science, AI, if you want. And I did a bunch of things during the PhD, but mostly I focus on active learning and bandits. Bandits is a subset of reinforcement learning, or like a simple reinforcement learning, if you want. And active learning is how to collect data sequentially, taking into account what kind of data could provide you with more information, right? Again, this was more on the theory side. Again, proving theorems, some simulations, but nothing. It was not very, coding oriented, I would say. I also did a bunch of internships in research labs, and that's when I realized that you could keep doing research in these type of areas, but in companies, right? Which definitely was not obvious to me when I was an undergrad or master student. When I finished my PhD, I joined Google Brain, which is basically Google Research, is very similar in many aspects to academia. And first in San Francisco, now in Zurich. I'm in Switzerland, where we have a big office. And I've been working on a bunch of different things. At the beginning, pretty much what I was doing during my PhD, but more applied, more with, actually training models and so on, reinforcement learning, and again, bandits. Then I would say I probably lost a bit of my faith in reinforcement learning, even though I think it's a central topic and something we should definitely develop. I think we are still in very early stages. And then I pretty much attending to the rest of the people near me, I kind of got interested into generative models, representation learning, which I guess is everywhere. And now for the last couple of years, I've been working on special types of deep networks, mostly applied to computer vision, which is something I hadn't done before, ever. So that's just a bit of a summary. So if I had to summarize where I see machine learning, or what I think has been the trend or the type of progress we've seen in the last few years, I would go with the bitter lesson. Rich Sutton is a very famous Canadian RL researcher who wrote like a brief blog post called The Bitter Lesson. I invite you to look it up. It's very easy to find. And he obviously has way more experience. And I think here I copy pasted a couple of sentences from the write-up. He basically says that the bigger lesson in the last, he says 70, but a bunch of decades of AI research is that general methods that are friendly with like big amounts of compute usually win, and they win by a large margin. So, I'm definitely simplifying here, but if you think of algorithms, maybe there's these two big families of algorithms. One, I call them here scalable algorithms. The other ones, maybe is not the best name, but human-centric algorithms. So, and definitely what Rich Sutton is saying, that scalable algorithms are, or they have been, at least so far, a better bet. And these algorithms are general purpose, like they work for many different problems, and most importantly, they are fast. And this is something I'm realizing more and more. Obviously, now I work in a company, and the research, even though it could be very fundamental research, at the end of the day, the hope is to end up being useful, right? And time seems to be a major constraint, right? So you need fast algorithms, not only to make them work, but maybe to to let a lot of people get interested into them, and that way like further develop, right? So fast algorithms are like key, I think. And in order to be fast, you basically need simple algorithms, right? On the other hand, and maybe in the last few decades, these used to be the type of algorithms that were more successful. You have these, I call them human-centric algorithms, that are very problem-specific. They are usually very complex, and that leads to them being slow. And in order to solve this very specific problem, these algorithms exploit some field knowledge, right, from experts in that specific type of problem, right? I mean, again, this makes a lot of sense, right? But I would say these algorithms have been losing a bit a lot of domains, right? On the side of scalable algorithms, there's two main techniques that have been very successful that satisfy, I mean, two main meta algorithms that satisfy many of these checkboxes. Those are search and learning. And by learning, I guess I mean automatic differentiation kind of algorithms. So here I give you a few examples. I'm not familiar with all of them, but for example, I mean, everybody knows about chess and Go. And at the end of the day, if you think about it, like maybe, I don't know, 40, 50 years ago, there were like chess and Go experts that could encode what they knew about the game and hope that would, I mean, if you put together that with some kind of massive compute, that would be useful, right? But then a search algorithm like MCTS, which is some kind of statistically smart brute force search algorithm, was able to beat by a large margin these algorithms, right? And I guess this connects with the second sentence I copy pasted here from Rich, which basically says that we want AI agents that rather than just containing what we know, can learn by themselves or get some insights that they find more useful, right? However, in these scalable algorithms, you still need some inductive biases. I'm not saying we should not encode anything, right? For example, if you think about computer vision, things like convolutions, they basically are, we realize that images contain information in some ways, right? So we encode information in some ways because we are familiar with images, right? Or perception, human perception, right? If tomorrow you randomly permute the pixels in an image, these inductive biases would not work anymore. So even though there's people trying to get rid of every inductive bias, I think definitely some inductive biases are useful, right? And I think most of the shiny results we've seen in the last few years can be accounted to three big pillars: compute, models, and data. The first two are usually, or they've been so far, very linked to each other, very related, very dependent. So more compute is required for larger models, and larger models require more compute. There's some counterexamples, but that's kind of the rule. And more data is a different dimension, but obviously we've seen in the last few years, definitely companies, they have like huge amounts of proprietary data, but even like open source data sets are growing in number and size. And in order to develop and train larger models, you need more data. Hardware has played a huge role in this kind of revolution. It's been central to it. This is a picture of a bunch of TPUs. TPUs are basically computers that we develop at Google to train models, machine learning models. And in order to train these larger, the large models we've been using lately, we actually require this type of hardware. Otherwise, it wouldn't have been possible. A natural question is, okay, so scale has been working so far, but is it just all we can do? Is this the way to go? And how far can we go, right? By just creating like bigger models and more efficient hardware? The answer is, I don't know. Definitely, we've seen that in the last few years, models got better and they got more expensive in terms of flops, if you want, or in terms of energy required. And not only that, but maybe, and I'm not 100% sure, but every extra unit of performance, or if you want accuracy, or the opposite of error, if you want, has been more and more expensive, right? So what's going to happen next? Obviously, with this hardware, we cannot keep scaling things in the same way. But on the other hand, one could say that the hardware itself make it better. Actually, I think the last, we have had like several versions of these TPUs, obviously better and better over time. And I think the last one, we developed it internally with reinforcement learning. So we learned how to place, I don't know, transistors in a chip or something like that. And in some sense, the hardware could also like unlock things that today are not possible, right? And I think in these predictions, those things are not accounted for. In any case, what I want to briefly discuss is the type of work I've been doing and my team, I mean, my teammates and I have been doing in the last few years, which is one way to mitigate some of these issues. I'm not claiming it's the only one. I'm actually not claiming it's enough, but one way to decouple computation and model capacity or model size. So again, very simple. If you think about it, here, I mean, the plots I'm trying to show like 3 neural networks, if you want, deeper and deeper. The deeper the network is, the better you do. So that's what I try to show with these sticks. And obviously it takes longer, right, to run those models. So usually more parameters, so a deeper network requires more compute. And more compute requires more time. The second thing, in principle, if you had better hardware, I mean, you could, for the same amount of compute, you could do it faster. Still, less compute will require less time in that case also, right? But the question is, can we focus on the first thing? And that's the promise of what people call sparse models. Can we scale the model capacity, so make bigger models, but keep the computation constant? And one picture that could kind of convey that idea is the following, right? So here again, we have 3 models. The size of the models is different, right? In yellow, what I show is kind of which parts of the network are activated for a specific input. So you see that on the first one, which is what I would call a dense model, we activate everything for every input, right? But in the second and third, we only activate some parts of the model, in particular, let's say 1 per layer, so that the total amount of compute is the same or very similar in every case. However, you, in the second and third type of model, you still have way more capacity, right? Which in principle could improve performance, right? If the model is able to use this in the right way. So, I mean, now in the context of specifically of deep learning, the idea here, like trying to simplify this a bit, is like different inputs follow different paths in the network. How do you decide those paths? Well, you have routers that make decisions for every input, and those routers are also like small neural networks that you train together. So you train, let's say, everything simultaneously. The whole idea is definitely not new, right? If you think about decision trees are sparse in this sense, right? Because if you have an input and you're in a node and you need to make a decision, let's say left or right, if you go to the right, then all the parameters that are in all the nodes on the left side are not used. I mean, they are not applied to this input, right? So this idea is very natural. But in deep learning, it hasn't been explored in depth yet, I would say. Again, to explain how this would work, suppose you have a deep network, you have 2 data points, let's say the yellow and the blue. There's some dense layers that are applied to every data point, like layer 1. But then for layer 2, you want to have a lot of capacity, but you want to constrain your compute. So you have a router that takes the yellow input and decides to send the yellow input, let's say, to 2 blocks out of the 6 blocks that we have here, right? And then you need to combine the output of every expert. We call these blocks experts. And then the network kind of continues mixing like dense layers and expert layers. And here you are selecting 2 experts per input, but in principle, you can even select 1 if you want to mimic the same compute as the dense counterpart. And a lot of people, mainly I would say at Google, but also in other places, have been trying this in the last, let's say, couple of years, and it's been quite successful. In language, this allowed to train like trillion of parameters models that can achieve the same performance as a dense one with a save of speed of 7x, for example. In vision, we've also developed something similar where for any amount of compute, these type of sparse models can deliver better performance. However, this is quite kind of not very mature direction, so there's a lot of open questions and a lot of challenges, right? The first one is the hardware that we have right now is not ready. And these models are so large that they do not fit in a single machine. So you need to distribute the whole model. And the problem is when you have an input that the router decides to send to expert 7, maybe you need to send the data through the network to go and apply expert 7 or things like that, right? So this requires super complex engineering. And I think because of that, all these ideas are still in the research stage, but they are not ready for being applied to real world, to production systems, let's say. Another thing, and I guess this is the reason I got interested into this, because this had to do with my previous research. This has a decision-making flavor to it, right? So there is this exploration-exploitation dilemma. So if you start training from scratch models like this, very quickly the router will decide that, will send the data points to a very small subset of experts, to very few experts, because those experts will get updated or get trained a bit, and they will have an edge over the rest of the experts, and the rest of the experts will be useless to start with, right? And the router will keep choosing the very first experts, right? So that's over-exploitation, let's say. And these routers, they need to make the discrete decisions, right? Because you need to select a subset of the experts. You cannot send the inputs to all the experts. And discrete decisions are usually difficult with the kind of standard continuous gradient descent type of methods that we use. In addition, there's a non-stationary aspect to this. So if you're learning to play chess and you play one game and you lose because you do stupid things at the beginning, the next day you play the same game, right? The game doesn't change. But in this particular type of setup, if you start choosing the same experts, you change the rest of the model, and the model may never recover, right? So it's not like the second day you play the same game from scratch. You are changing the environment, the game itself. It's a bit more difficult. And well, there's a lot of open questions about how to transfer and fine tune these models, but I want to talk more about that next. Okay, now a bit disconnected from what I just described. If I had to summarize some general trends I see in applied machine learning, I would choose the following. I think I've selected 3. The first one is the transfer learning, which is something kind of new to me. Maybe it has a long tradition, but I didn't know about it until a couple of years ago. But I think transfer learning will be a big player. And it's because it makes sense from, some sort of economic perspective, right? Just for the people that don't know what's transfer learning, you have usually an upstream data that is massive. You train from scratch a huge model. This is usually expensive. But once you have that model, you can specialize the model to a number of downstream data sets or downstream tasks that have some sort of relationship with the upstream, right? If they are completely different, then this may not work, right? But the idea is that if they have something to do, you can now just take the model and fine tune it, which basically means you keep training from the original model, or you can freeze part of the model and just train a small subset of the layers, or even just the last layer, which is very cheap. And it's not, so the whole point is not just that it's cheap, but the whole point is that the representations that you learn in the first place are very useful and can deliver a really good solution for the downstream task. And if you were training just the downstream task from scratch, you would not achieve such numbers, right? Here I give a couple of examples. So you can train first on all of Wikipedia. So you see a lot of sentences, and then you have a bunch of text tasks, like, e-commerce web reviews, which is a very specific type of, writing, but still respects the type of sentences that you saw in the Wikipedia article, and you can just fine tune it to it, and this will work very well, right? And I can see a lot of companies, cloud services that can offer this as a service, right? So you don't need to share your upstream data, and also maybe your customer that has a small data set doesn't have the ability, the know-how, or the data to train from scratch, so you can offer this as a service, right? I think this is important, and the models that we develop need to be transfer learning friendly, which is not always the case, right? Another thing I've seen, and I see a lot of momentum, is multi-modal models. Multi-modal means models that handle simultaneously several types of data, let's say images and text, or video and audio, right? And things like that. The reason why this is important is because I think the type of tasks that we will try to solve in the near future usually involve usually requires several types of inputs, like perception inputs, like, I don't know, self-driving is an example, or something with videos, like video tracking, or subtitles for videos, and so on. And in addition to being important, I think there's a lot of potential here. So, I mean, I think today, after my talk, we will hear about causality. Causality is the real game. But while we try to learn how to solve that, here we are basically trying to exploit some correlations, right? And I think when you have different types of inputs together, there's more correlations to exploit, right? I mean, we are very surprised. I mean, we've been very surprised in the last few years by the amount of correlations we can exploit in one type of data models, like images. So imagine if we could merge several of them, right? Here I'm giving in the plot, you can see an example where you have an image and a caption, right? And or a question, which is text, and you try to answer that, right? So I think this is we are gonna see a lot of these models in the near future. Finally, the third thing I would highlight maybe is self-supervised learning, which is a very simple thing. You have some data, usually it's unsupervised, so maybe you don't have a specific answer or label or thing you want to predict, but you can create a proxy supervised learning from the unsupervised data because you know what's the answer to that problem. And by doing this, you can suddenly train a supervised model, and those represent, and obviously you're not interested in that specific artificial problem you created, but those representations that you can train are maybe very friendly for this type of transfer learning to other specific tasks on which you have fewer supervised data. And here I give a couple of examples. In language, you can take a sentence and remove a random word and then try to predict it. And we have a lot of sentences, right? And in images, you can maybe do something like this, where you partition the images in patches, and then you shuffle those patches, and then you try to predict the right order because you know the right order. And for videos, you can, I don't know, sample frames and try to predict which one goes first and things like that, right? And I think all these ideas will probably at some point be combined at a large scale because the amount of data is going to be probably very large, right? So we will require like models that can handle so much data, therefore they need to be probably large. So just to wrap up, some tips for ML students, or if you want people interested in an ML career. So, okay, so the first thing I've seen, and today I'm talking about like deep networks and the latest models and so on, but still, I think, especially at the beginning, like, I don't know, as an undergrad, even as a master's student, my personal advice is stay away from things that change every week and try to focus on the basics, right? And a strong background, I think, is very important, even though that may not be the thing you want to do in the next 5 years, but I think it will pay off. Things like, I don't know, mathematics, algorithms, coding, and even understanding how computers work can be very useful. Second thing, one thing is ML-related careers, and another thing is research ML-related careers, right? Not everyone needs to work on research. So, but if you want to work on research, or if you think you may enjoy it, I think as an undergrad, as a master's student, probably it's a good idea to get involved in some research projects just to understand the feeling of trying to tackle a question for which you don't know the answer. Again, there's no need to be the first or main author. It's actually better to work with other people, and you do not need to do sophisticated stuff. The question is whether you enjoy it or not. And if you want to apply to things like masters, PhDs, or even like jobs at the research industry, I think there's a lot of value in showcasing what you've done, right? Having some sort of artifacts. It could be open source code. It could be a blog post about a paper you read. It doesn't need to be your paper. Definitely you can write papers or reviews of other papers, summaries, side projects that just implement something. I think there's a lot of value to apply to places, and a lot of value for you to understand things much better, and also like realize whether you like it or not. And finally, I think if you are still, I guess the last thing definitely applies to people that already have jobs, right? But may want to change jobs. But if you're still a student, I think things like internships are a fantastic way in the sense that I think it's better to go there, spend some time with people so that people know you and maybe later come back. And also they offer you the possibility to spend, I don't know, 3 months, 4 months in different places and see what you like, right? As a general advice, I don't know, if you know people that are, I mean, if you see people that are where you want to be, just ask them to chat, have a coffee, and people are usually very open and friendly. And I think that's all I had. Thank you so much. And if you want to reach out anytime, I'm happy to talk to people.
Thank you so much, Carlos. It was an awesome presentation, really helpful as well. So what we're going to do now is just open the floor to questions. So we have a couple of them coming through the chat, through the Q&A section of Zoom. And Manuel, I'll pass it off to Manuel.
Yeah, so we'll wait a couple of minutes to see if there are more questions. But in the meantime, I think I can address the first one, which is about the slides. We didn't intend to share the slides, but this webinar is being recorded and it's going to be uploaded to YouTube. So we'll share the link later.
Also, I'm also happy to share my slides. If anyone wants them, they can send me an email, and I'm happy to share them.
Okay, yeah, that's another solution. Okay, so I can go with the first question, and it's Diego that says, I saw the documentary called The Social Dilemma, and it seems that algorithms in social media are out of control in a sense. Because they viralize fake news and hate remarks, which are not good for our society. In that way, how can we control what algorithms do and not let them ruin us?
I guess that's a good question. I mean, algorithms do what you ask them to do, kind of. So if you try to optimize for some metric, the algorithms will try to find the easiest way to do so. So probably as a society or, I don't know, different organizations should try to think what's the right thing to optimize. I mean, it is true that there's a wide range of people, at least, for example, in my research team, there's a wide range of people working on things like fairness, ethical AI. I'm not an expert in the topic, but definitely something that I think is quite obvious is if the data set contains some biases, let's say, the algorithm is going to probably replicate those, right? There's people trying to avoid that. There's at least 2 ways where you can try to tackle that. One is trying to collect the different data, or like basically focusing on the data collection. Another one is to try to keep the data the way it is and try to modify the algorithm to do something different, or to not use subsets of the inputs and things like that. And I think there's been work in both directions. Another very, large research avenue is explainability. So many of these models end up being black boxes, right? So I don't know, if you think about clicking ads or clicking or recommendations and so on, we can summarize a model by some kind of metric, like, I don't know, click-through rate or things like that, right? But sometimes it's not even easy to understand why those algorithms output those decisions, right? So there's a bunch of people trying to, or even, let's say, a less controversial case, right? Like for medical diagnosis, I mean, we do a lot of work on the medicine side of things. And if you imagine a future where tomorrow you can go to the doctor and the doctor will talk to, introduce your data to a computer, and the computer will say X or Y, most likely the human will want to know why, right? And I think at this point, we do not have good answers for that. I mean, we just say, okay, because the model says so, and the model is usually right. But I think there's a bunch of people trying to, to shed more light on why things are happening, either by highlighting parts of the input, or by aggregating, clustering inputs, and I don't know, trying to provide maybe not even the final person or the final customer, but like some type of man in the middle that can work with the computer to give an answer and an explanation. Obviously, and this is a different thing, and maybe I'm talking about lot of different things. But there's a problem with deep learning where basically we rely on point estimates, so we do not take uncertainty into account. I mean, there's obviously a lot of people working on this, but I think that's going to be very important if we want to move away from ads and recommendations and really start handling like critical decisions to computers, like driving or medical things and so on, right? We need to have a sense of uncertainty, and I think we don't at the moment.
Thank you. So, by the way, if you guys want to follow up any question, just send another one and I can link it. So there's another question by Alberto that says, regarding transfer learning, new visual transformers pre-trained models have been developed over the years. And do you think these will replace traditional convolutional networks?
In the short term, definitely. I think there was this paper, and actually it was by some people in our group that came out, I think last year, applying the transformer idea that was already very successful in language, applying it to vision, where you take an image and you partition the image in patches, and every patch is a token and so on. And it's been very successful. And there's been a lot of follow-up work. Is it the final answer? Probably not. Is it a good step forward? Yes. Why does it work? I don't know, but I mean, it could have more to do with the way you partition a huge input like an image into smaller tokens than the way you process them in a visual transformer, which is with attention and so on. I mean, I think sequence learning seems to work very well. And for language, that's very natural because you have words, let's say. For images, maybe it's also natural to divide the image, or for videos in frames, right? But so far, I don't think people had explored that so much. And now it seems that people are exploring that. But convolutions probably will also be useful.
Thank you. And I actually think, Juan, you had a question. So you can, go ahead.
Sure. I'm by no means an expert in the topic of neural networks. I actually don't use neural networks at all in my research, but I found it very interesting before you were talking about one of the advantages of transfer learning, that you can train these models with huge data, and then you can just share the model and not the data, which is advantages if you're a company and you have this pool of private data that you want to keep. But I guess these models to some degree reflect the data that they've been trained on. Is there some sort of vulnerability here, or sort of privacy concerns? Is this something that, I understand this is something that is studied in some settings. I find it super fascinating. And if you know about it, I would be super happy to hear your thoughts on it. Thanks.
Yeah, I guess you are encoding your data in a model. And this model, the thing is, before maybe you had a linear model and you could just, summarize the very high level key aspects of the data. But now with trillions of parameters, sometimes these models are actually memorizing part of the input. So that means that, for example, if you care about privacy aspects, it may not just be enough to not share the data, but share the model. The model still contains a lot of knowledge from the data, right? There's a bunch of things people do. You can add noise to the data while you train. You can even add noise to the model itself. I think those are like cheap tricks. I don't think that's going to solve the problem. There's people that have seen that you can very easily attack all these kind of models by just changing a bit the input, and then the model is totally confused, which I guess that says that the models are not robust. And that can be a big problem, right? Let's say you have a self-driving car, and the model that decides what to do is vulnerable to these attacks, and someone, puts like a sticker in a stop signal, right? Then maybe the model thinks it's a washing machine or is nothing, right? And it continues, right? So definitely those are important questions. I know there's a lot of people working on this. I'm not an expert, but definitely the models retain a lot of the data. So that's something to take into account. Yeah. By the way, if just one follow-up, if you want to do transfer learning, you don't even need to provide the model, right? You may just retrain the model yourself with the new data and just provide predictions for new inputs, right? But again, if you think about inputs are like queries. So you could use queries to figure out what's going on in the model, or even like try to recover parts of it. So that's still problematic.
Great. I think Ines now has a question.
Hey, Carlos. So a question just building off of what you were talking about transfer learning. I would be curious to know, is there a particular domain that you would say where transfer learning is, has potential? I've seen, at least for me, I've seen a lot of transfer learning in terms of NLP, a lot of things going on there. But do you see anything, any particular domain, anything where, you could see transfer learning as trending? It's a broad question, but.
Yeah, I mean, definitely if you think of one type of data like NLP or images or video, which is very related to images, I think transfer learning can work very well as long as the tasks you're interested in are or resemble a bit the upstream data. Even for things like reinforcement learning, I mean, I haven't worked on this for a while, so I'm not up to date. But my understanding is transfer learning works very well in the sense that you can, I mean, if you have access to a simulator, you can, get a lot of data from the simulator without maybe making very smart decisions, and first pre-train something that just maybe solves a proxy problem, right? To get representations that are useful, representations that take a concept that could be useful for a task and give you a vector of numbers that is far away from very different tasks and has some kind of arithmetic properties, right? And then you can use that as a starting point to apply a standard reinforcement learning algorithm, right? So, and the thing is, once you combine this multi-modal type of data and multi-modal models with transfer learning, maybe you can have like a single huge massive data set that covers a lot of use cases, right? I mean, still, if tomorrow you come with something, a DNA type of data set, maybe there's absolutely no connection, right? But as long as there's some connection, I think transfer learning can help. And the thing is, transfer learning doesn't need to completely solve the new problem. Kind of what we need is that it's better than training from scratch. And I think that's going to happen in many domains.
Thank you. So there's some more technical question from Uriel, who asks, can you share more details on how do you train the routers if possible? Do you use bandits-like methods to do that? Is the network agnostic to those choices in training time?
We do not use bandits. We thought about it. But the thing is, I guess, the bitter lesson applies still, and bandits algorithms could be also very slow. So even though bandits can solve some of the problems with exploration, I mean, the thing is, in our networks, we do not have one layer with these experts, but we have a bunch of them, right? So bandits do not directly apply in the sense that you do not, so for every input, you do not make one decision. We have models where you have 45 layers, out of which 20 have experts. So that means that you have 20 routers, and the same input goes through all the routers. So you make 20 decisions in a row. So in some sense, it's no longer bandits where you, let's say, make one decision, but it's a sequence of decisions, and the 11th decision is influenced by the first 10, right? So it's not that simple. I think, we're still open to consider ideas like that. And I think our routing, we still don't even know how good is our routings, right? So they work, they learn useful things, but we don't know if we can develop like routers that are twice as good, or we are almost there. So we're still thinking about it. At this point, we do things that are not very smart because these routers are not fully differentiable. So we need to apply some proxies and things that are not very efficient, but at least they are fast. And I think, unfortunately, at this point, fast ideas are more useful than smart ideas, like bandits, for example.
Great. There's another question from Fernando that says, regarding uncertainty, since you come from a bandits background, I'd like to know what you think is the most promising way to go now.
That's a good question. There's a lot of work on Bayesian deep learning, which is definitely exciting. The problem, my understanding is that the problem is that so far, again, it doesn't scale. So these methods, so there's a trade-off, right, between I guess, accuracy and speed, right? If you want to be very accurate with the distributions, then you need to invest a lot. And at this point, the models that in that trade-off favor like accuracy and doing the right thing are not competitive at the end. So the approximately correct approaches, because they are much faster, they end up winning the race. I'm not saying it's good news. I'm not saying it's going to be that way in the next few years. Maybe there's a breakthrough that changes the outcome. But at this point, I feel that's how it works. Yeah. I mean, I think a lot of people are working on approximate inference and things that are not correct, but they offer a sweet spot in the trade-off. And I think that's probably the way to go.
So we don't have any more questions in the Q&A. I don't know if anyone in the panelists has any more questions. Otherwise, I think we could move on to Juan. And then if you guys have any questions for Carlos, I think you could still input them in the Q&A with some reference if it's for Carlos or Juan. And so Ines, if you want to take over.
Okay, great. So let's pass it off to Juan. Juan, feel free to share your screen whenever you can.
All right, so give me a hands up if you can see my slides.
Yep, we can.
Awesome. All right, so I should start by saying thank you to the organizers. I'm always very eager to talk to people about causality, so thanks for the opportunity. I've been asked to say a few words about myself. So my name is Juan Gamilla. If you're going to search for me online, you should put that L after my name, or you will run into my dad, who is also called Juan, but publishes in a completely different field of research. I've been a PhD student for a bit under a year at the Seminar for Statistics of ETH, which is the German acronym for the Swiss Federal Institute of Technology in Zurich, where I just found out it's also where Carlos lives. I was born and raised in Granada. I did my bachelor's in mathematics and computer science at the Technical University of Madrid. And after working for a few years, I really wanted to go back to school to become a scientist. So I applied to a scholarship to today's hosting institution, but they were unfortunately not very convinced. So luckily, La Caixa was there to break my fall, and they funded my studies at ETH. My master's was a bit of a time of soul searching and trying to look for a field that really resonated with me, that I felt I could conceivably spend the rest of my life working on. And at the end of my studies, I came in contact with causality through a course that one of my supervisors was teaching. And when they offered me a position to stay and do my PhD, I accepted. And now I'm doing my PhD there together with the Causality lab at the University of Copenhagen. These are my lovely supervisors, Christina Heinze-Deml, Peter Bühlmann, and Jonas Peters at the University of Copenhagen. And I have to thank them for what has been so far a wonderful PhD experience. That pretty much wraps up what I have to say about myself. Overall, I'm really excited to talk to you guys today about causality. I've tried to remove all the technical details so everyone can follow along. So yeah, let's get started. So causality is perhaps a concept that we all understand very intuitively. We all understand the effects that our actions have, at least some of them. And we use this understanding to make decisions. For example, if we're riding our bicycle or driving our car and we want to slow down, we understand that we might achieve that by pressing on the brake. If our head hurts, we might take some aspirin to alleviate the pain. And we're able, very intuitively to tell apart these kind of relationships of cause and effect from relationships of mere association of things that happen together. So for example, when we're riding an airplane and the seatbelt sign turns on, and a few moments later the plane goes through turbulence, we understand that it wasn't the sign turning on that caused the plane to shake. We could also say that causality underpins the way we assign blame and responsibility, and so plays a role in our morals. We think in counterfactuals when we say, well, if this person hadn't done that, something else would have happened. And so these are all clear examples of causal reasoning that we do very effortlessly in our day-to-day lives. And so it's easy to argue that causality somehow plays a fundamental role in our human cognition of the world. And the question that I would like to ask you today is what role causality plays in science. And obviously, many of the questions we ask in science are causal in nature. For example, in medicine, we may ask about the causes of a certain disease, so we might treat it. In the social sciences, whether a policy was effective or not. And in general, we say that we've truly understood a system or a phenomenon, not when we're only able to describe it, but also to predict the effects that our actions will have on it. And for these kind of questions, causality is the fundamental concept. Whether the system you're studying is a cell's metabolism, the global climate system, or a particular social process that you're interested in. And I could keep going on and on, but the point I'm trying to make is that in many domains, learning the causal relations within a system is the ultimate goal of scientific research. And if you understand the scientific process to be in part learning causal relations, the question that I would like to explore today is whether this process can be automated. So of course, this sounds maybe a bit abstract at this point, so let me specify what I mean. So in many areas of science, particularly in the hard sciences, the way we build understanding of a particular phenomenon or process or system goes a bit as follows. So we might formulate some hypothesis as to how the system works. Based on that, we gather some preliminary data, and then we interpret this data, we reject our hypothesis or refine it. We may additionally think of additional experiments that are useful. We gather more and more data and repeat this process over and over again until we've reached a conclusion about how the system works, which is generally a statement about the causal relationships that underlie the system. And so what I'm proposing here by automation is to take the humans in this part of the process and substitute them by a machine. So the machine now does all the interpreting the data, keeping track of all possible hypotheses that explain what we're seeing, is able to select experiments that are informative. And after a few rounds of this experimentation, makes a statement or gives us its hypothesis about the causal structure that underlies the system, or more importantly, it can also tell us, hey, there is an important variable here which is driving the system, which you're not measuring. And then this decision of what that might be is left to the human scientist and their intuition and their knowledge of the system that they're studying. And so if you ask me if I think this would be possible, of course, I say yes. I wouldn't be talking about this otherwise. But my opinion comes with a few caveats. So I think there are some important challenges. The first one is that causal inference is a tremendously difficult problem. In many situations, it's simply impossible to recover any sort of causal relationship. And our success depends crucially on the kind of data that we have. And so this already limits the kind of settings in science that we might study using these kind of automated methods. The second problem is that I believe that the methods in my field are not quite there yet. And don't get me wrong here, I think there's been a tremendous progress in formalizing and mathematizing causality, which is a tremendously difficult question in itself. We also have some algorithms which, given data, are capable of recovering cause-effect relations. And we've successfully applied these algorithms to some particular systems. But I think we're still very far away from recovering causal relationships in a way that is reliable and transparent enough for a researcher to use in guiding their research. particularly when this might entail spending thousands of euros or hundreds of hours pursuing a particular experiment. And so what I would like to do for the rest of the talk is kind of convince you of this opinion and these caveats. So the first thing I would like to do is show you why causal inference is a difficult problem. And to do this, let's think about the following experiment. So imagine we have a new COVID vaccine and we want to study its effectiveness. And so we come up with the following study. We make it available to the general population and people can decide to get vaccinated or not. Of course, this is just a thought experiment. This is, for very obvious reasons, not how we do it in real life. But assume now we measure two variables, whether a person was vaccinated or not, and whether they contracted COVID after a certain amount of time. And we measure the infection rate among the vaccinated and find it to be smaller than among the people who were not vaccinated. And so now we may ask, okay, how do we explain this observation that we've just done? So the first hypothesis that we may come up with is that the vaccine is actually completely ineffective. It's simply because the vaccine is participating in the study and getting the vaccine is voluntary. People who are getting vaccinated are people who are already concerned with the disease. And so they're already taking measures as washing their hands and wearing a mask in public spaces. And so what we're actually measuring here is simply the effect that concern has on contracting COVID. The second hypothesis, which is perhaps the one that most people would imagine, is that the vaccine is indeed effective and it reduces the chances of infection. Now the issue, and this is the key idea why causal inference is difficult, is that given the data that we just have here, where we measure only these two variables, there is absolutely no way to tell these two hypotheses apart. They're both equally valid when it comes to explaining what we're seeing. And it's also not a matter of the amount of data that we have. We might make a bigger study, but we would still not be able to tell these two hypotheses apart. And so now you might say, okay, but we have vaccines in the real world and they work. So how was this done? Well, of course, the answer is through what is the golden standard in modern science when it comes to inferring a causal effect, which is the randomized controlled trial. So I'm assuming mostly everyone here is familiar with what this is, but just for safety, this is a study where we have a study population. We split it at random into two groups, and then we treat one of the groups, leave the other one untreated as control, and then we compare the difference in the outcomes. And so the key assumption that we're enforcing here by doing this random splitting is that the only variability, the only difference between the control and treatment group is actually the treatment. And from this assumption, we can infer that the change that we observe in the outcome is actually caused by the change in the treatment. So randomized controlled trials give us a very trusty way to infer causality. Of course, designing a proper randomized controlled trial is an art and a science upon itself, but it constitutes our first tool of doing inference when it comes to recovering causal effects or studying causal effects. The issue, of course, is that we cannot do randomized controlled trials for all the problems that we care about. It might be too expensive. It might be unethical. We cannot ask someone to smoke 20 cigarettes a day for 20 years just to see what effect that has. But more importantly, it might simply be that we're studying a system over which we don't have such tight control. And so we cannot perform these very precise manipulations like we do in a randomized controlled trial. So we might ask, okay, is there any hope of doing causal inference, of learning cause-effect relationships from other kinds of data? And so if we go to the other side of this data quality spectrum, we find the data that we would find from an observational study. So this is, by the way, the setting for which the Nobel Prize in Economics was awarded this year to these two researchers from Causal Inference. And just to give an example here, so it's not too abstract, this is the kind of data, for example, that people look at very often in economics or development studies. So for example, where we would look at the decrease in child mortality over the last few decades, we would measure a lot of other variables, socioeconomic indicators, development indicators, and we would try to ascertain which variables drive this decrease in child mortality. On a more abstract level, what we're doing is, this is the kind of data we have from a system that we observe without the system being manipulated. And this is the setting that has been studied the most in causal inference in my field, and has given way to a framework that we call causal graphical models. And causal graphical models gave us a way, first, hard limits as to what we can learn from these kinds of data. Not everything can be learned. There are simply, as you saw before, causal relationships that cannot be told apart. And they also gave us our first few algorithms that in this path of learning causal relationships from data. And so I would like to go now a bit into detail about how these algorithms work, just to give you an idea. So you appreciate the great ingenuity behind them, but also the shortcomings and why I say this thing that perhaps we're not there yet in terms of methodology. So to do this, let's refer back to the COVID example. So what happened here is when you observe this difference in the infection rate, what we actually discovered was that these two variables, being vaccinated and getting COVID, are actually linked. They are dependent. And of course, correlation does not imply causation. But what people did in the field was to ask, okay, what role does causality play in creating these dependencies? And so one of the first things people did was to say, okay, if two variables are dependent, if we observe a link between them, this means that either one variable causes the other, or they're linked by a common cause, which affects both variables and drives this dependency. And so in our search of rules of trying to learn causes from data, we might call this our first assumption. And it's an assumption because this dependence could still be a spurious correlation. Many processes in time, for example, how bacteria double, if you look at them, they will always appear correlated. It could also be that we're under selection bias, so that we're introducing this dependency artificially in the way that we collected the data. And then as a second assumption, we might introduce the counter statement. So basically we would say if two variables are independent, then there's no causal effect between them. And then people added a few more assumptions, namely, for example, that there are no causal loops, so that if X causes Y, then Y doesn't cause X. And another assumption called causal sufficiency, which basically means that we're measuring all the relevant variables, that we didn't forget to measure something like concern in the COVID example. Now, all of these assumptions have names in the causal literature. And of course, there are some that you might not agree with. And I agree with you, there are some assumptions here that do not apply to all systems and to many systems that we might be interested in. But they might apply to some systems. And furthermore, these algorithms gave us a first foothold into this path of developing algorithms to learn causal relations from data. So let's see a bit how an algorithm like this would work. So again, the setting is we observe a particular phenomenon, we get data from it. We measure some conditional dependencies in the data. And then we feed these dependencies to our algorithm together with the assumptions we've made about the kind of causal models. And so what this algorithm would do now is it would search over the space of causal models to try and find those which can explain what we're seeing. So what you see here is, for this toy example of 3 variables, all the possible causal models that exist when we eliminate the possibility of cycles. And they're ordered here by the number of edges of causal effects. So 1 at the top, 2, and then 3. And so what the algorithm would do is it would, for example, start with the measurement that X and Y are independent. And so if you remember our second rule, this would mean that all these models where there is X and Y are connected, so either X causes Y or Y causes X, all of these models are not valid. And so we might remove them. We would then measure X and Z to be dependent, which means the contrary. So these models where X and Z are in no way connected are no longer viable explanations of what we're seeing. The same goes from when Y and Z are dependent. And then if we look at these last 4 models, for example, this one, we see that X causes Z, which in turn causes Y. So X does have an effect on Y, which means that we would expect X and Y to be dependent, which goes against as a contradiction with this independence that we've measured. So we might remove this model. The same goes for this one, which is the same in reverse. And this last one is one of the definitions we gave for dependence, basically that X and Y are linked by a common cause. So we might also remove it. And so after all this, we're left with a single model that explains the data that we're seeing. Of course, at this point, you might say, okay, this was all a bit too easy. Something's a bit fishy here. And you're right. There is a limit to what we can learn from observational data. And these dependencies, I've picked them in a particular way that we would arrive at a single model. If, for example, we had measured, instead of X and Y to be independent, we had measured them to be dependent, we wouldn't have arrived at this model, but at all of these, and we would have not been able to tell them apart from data. The second issue with these kind of algorithms is that doing inference for larger systems where we have more variables requires measuring some complex sort of dependencies in the data, basically conditional independencies. And these are tremendously difficult to measure in practice. It's a very difficult statistical problem. And it's simply impossible for general kinds of data to measure these independencies. And this explains why these sort of algorithms, when we've applied them to real data, they have a loss in power and they tend to make a lot of mistakes. The third issue is that simply you might not agree with some of the assumptions that we've made. And this is a very valid concern. For example, this assumption that we've measured all the relevant variables might seem unrealistic. And in many cases, it is. How do we even know which variables are relevant when it's a system that we're trying to learn? Another issue, for example, this assumption that there are no causal loops completely rules out the sort of systems where there are feedback loops, which is arguably a fundamental building block of nature. So this already excludes the applicability of these algorithms. And so still, this was the work that was done at the beginning of Causality. And it has given us an idea of what we can learn from observational data. What I believe is way more relevant setting for this idea of automating science is data that might lie somewhere here in the middle. So basically, data that we have from a system as a system is being manipulated. And so this is, for example, data that would come from a setting where we can do experiments on a system, but our experiments might have off-target effects, and we might not have full control over which variables are being manipulated and how. It could also be data where it hasn't been us who performed the manipulations. Someone else was doing them. And so this is also a relevant setting for other areas of AI. And in this setting, this is a setting, that we've only started studying very recently in Causality. And a very cool idea that emerged is what is called Causal Invariance. Of course, I'm a bit biased here because this is the work that my supervisors have been doing for the last 6 years or so. But it's an idea that I would like to share with you because I think it goes more towards the setting of automating causal discovery in the sciences. So I was having a bit of trouble coming up with a way to explain causal invariance without getting too technical, because it's can get very technical very quickly. So I thought the best idea would be to look at a real example. So over the summer, I built a little toy system to test these kind of things. So basically, we have a wind tunnel. So we have two fans connected in series. One is pushing air into the tunnel, one is pushing air out. And we measure two variables. We measure the amount of power that we supply to each fan, and we measure the actual speed of the fan. Now, of course, this system has no scientific interest whatsoever. But the point is that it's a very simple system from which we gather real data, but we know the underlying causal structure, which is this one. So, of course, we expect that the power we apply to the fan affects how fast it spins. But what is interesting is then, because they're connected in series, the speed of each fan affects the other. And so here are some real measurements from the fans. So we can see here how the increase in power on this fan drives this one. But as the other one spins faster, we see a little bump here in the speed. And so the game we're going to play now to understand how causal invariance works is we're going to try to use it to recover the causes of the speed of this fan. Okay. And so on a very high level, the idea of causal invariance is that when you predict the value of something, of a variable here, by looking at its causes, your prediction will remain stable as you manipulate other parts of the system. This makes sense because you're predicting a variable based on the things that actually drive it. And so what we do then for causal inferences, we turn this idea around and we say, okay, if a prediction breaks down after you do some manipulation, then this is a strong indication that either you're missing an important cause or you've included in your prediction something that is not actually a cause. And so let's look how this would actually work. So here we're predicting the speed of the fan based only on its power. And so we see it works quite well. And then here suddenly there's this little bump that we cannot explain. And this is due to the speed of the other fan. So if we now include that variable, we can see now that we perfectly are able to predict the speed of this fan that we're looking at. So we take into account the speed of the other fan and its power. And so we're now able to perfectly track to predict the measurement that we're actually making. Now, of course, this looks very nice, but what is important here is to remember that causal invariance doesn't tell you whether a model is true. It doesn't prove causality. It simply tells you when a model or when you're actually missing something, when the model you've built about the system is not correct. And of course, this might all seem really nice, but as always, there are complications in practice. So the first one is that fitting these models might be a bit more complicated. Also, actually testing for invariance is a difficult statistical problem. But it's important here that it's difficult, it's not impossible. Of course, I could do this here because I know the ground truth, and so it was relatively easy to fit the models. The second issue is that what we can actually say in terms of causal structure is limited by the manipulations that we've done on the system. If we've done no experiments, anything we say seems like a plausible model. But I would like to argue that this is perhaps not an issue because it closely resembles the way we do science. In science, we don't say, okay, this model that we hold about this phenomenon is the truth. We simply say, well, it's a hypothesis that we have not yet disproved by any experiments. And so for me, this is an indication that we're perhaps going in the right direction. And this is also what I find hopeful is this is some of the work that I've done over the last year, is that you can actually, from looking at how models stop being invariant, you can actually select experiments which are informative. And so this seems to fit nicely into this setting that we had of automating this part of the scientific process, particularly in the hard sciences. So to wrap it back to this thing, I guess I've already shown you that, or I hope I've convinced you that causal inference is a difficult problem, and that there's very little we can do, or there's limits to what we can do when we look at observational data. But we have also seen that when we're able to do experiments, we're in a setting where we have data from manipulating the system, we're able to say more things. And I mean, this is not surprising because since causality tells us what happens to a system when we manipulate it, having data from these manipulations might give us insight as to the causal structure. The second issue was, of course, that causal inference is still a young field, and our methodology is not quite there yet. But I hope I've also managed to convince you that this is an active field of research. And so I guess some of you are either very skeptic right now or terrified at the prospect of machines doing science by themselves. So I wanted to make one last remark, which is that we have not fully removed humans from this process. In fact, humans are still doing the difficult stuff. Humans are deciding which variables are relevant to be measured, which might hold some causal structure and some information about the problem they're studying. They're also giving the machine the assumptions that it might make, which hold for the system when it's working. And so the idea is really to leave to the machine what it does better so that the humans spend more time doing what they do best. And of course, as with everything in research, this might prove to be a pipe dream, or it might be that it's a problem that is too difficult for our current times. But at least for me, the promise that we might be able to do science better and faster, and that we might ask different and perhaps more ambitious questions is a promise that is simply too large to ignore. Yeah, and with that, I would like to end. I'll take your questions now.
Thank you, Juan. So I think now we can wait again a couple of minutes to wait for some questions. So guys, if you want to ask anything, type in the Q&A. Okay, so I think I can start with the first question. I'm not really sure. So it's more about economics. So not my topic, but there has been a lot of debate between academics from economics and causality. The formers defend that potential outcomes is the only framework that should be used in economics, and the latter that econometrics has to use DAGs, which I think it stands for directed acyclic graphs. What is your opinion on this debate, if you have any, of course?
So thanks for the question, Roberto. I was kind of expecting it. So this is a good question. Perhaps, I guess, not everyone here is familiar with what potential outcomes are. So historically, in the beginnings of, let's say, modern causal inference, there were two ways to think about causality. One is this idea of causal graphical models, which I've just explained. And the other one is what is called potential outcomes. And the idea here is that the questions we ask in causality are better expressed in counterfactuals. So if we want to judge, for example, the effect that taking aspirin has on our headache, the question that we're actually asking is, what would have happened had I not taken the aspirin? And so this has its own difficulty, which is, of course, we only observe one outcome of every action that we take. We don't observe the opposite. But this has led to also another framework of methods, which is also widely used in econometrics. And so there are two questions at play here. I think, so the debate that Ruben and Pearl have very often is that, for example, when it comes to the causal graphical models, we assume that we can manipulate every variable. But for example, that if we're trying to ascertain the effect that gender has on income, that we can somehow perform an intervention on gender. And those are the kind of questions that we ask. But of course, there are a lot of variables which we don't even know what an intervention would mean. Like for example, this question about gender, what does it mean to change a person's gender in the data? Are you changing this person's gender at birth? It's very difficult to answer. And so the approach from the potential outcomes crowd is that you cannot ask these sort of causal questions because it's hard to, if you cannot do a manipulation, then it makes no sense to ask what the effect of that manipulation would be. It's a difficult, almost philosophical question, right? I think the truth, as always, is probably halfway through. So causal graphical models, on the other way, give us a way to think about these natural experiments for which, for example, the Nobel Prize was awarded this year. So even if we cannot do these manipulations, we can try to push a bit at the data and see what effect gender has when we control for other variables. And causal graphical models gives us a formal way to reason about which other variables we might control for. So, yeah, my opinion on this debate is, it's a difficult question. But yeah, I hope that answers your question, Roberto. If not, you have my email. You can always write me.
Yeah, and there is a follow-up question from Roberto as well. If the use of causal invariance requires experimental data, why not use randomized control trials instead? Is it because way less experiments are needed, or the idea is to use observational data where we know where the interventions took place?
All right, so I mean, this is a bit what I said before. It's simply not possible to do randomized control trials for all the questions that we care about. As I said, maybe because it's unethical or because we cannot control the system in such a precise way. But another important thing is that if you think about an RCT, you're testing a binary variable. The treatment, you're saying either treatment or no treatment. If the manipulations you can make instead of one are n, you have way more possible combinations of experiments that you can do. And this is what is called factorial experiment design, which is very expensive because as long as the moment you have only a few possible interventions that you can do, your space of experiments grows like crazy. So it's simply for many fields, it's just, for example, in biology, where already some experiments consume thousands of euros a week, it's simply not possible to do these kind of things. And so we still rely on the scientists that is doing their job to rely on their intuition to filter through these experiments and see what might be interesting. But the goal here is that perhaps a machine can do this in a better way. I hope that answers your question.
So there's another question from Carlos that says, you have mentioned science as a possible application area. Are there other obvious areas where causality might be particularly useful?
Yeah, I mean, causality seems to be a very fundamental question. Causality, I mean, there's a lot of people who are interested in causality, not for causality's sake, which is my case. Causality also holds a lot of insight when it comes to statistical modeling and to machine learning. Basically, for example, this idea of invariance already shows you that causality might be the key to robust estimators. When you make predictions based on the things that actually matter, you're less susceptible to errors of this kind, to distributional shifts, things like that. For causality itself, I mean, I see a very clear and very terrifying application, which is any place where you have a lot of data that you can also manipulate. And for example, all of the internet services that we use kind of have this power. They collect a lot of data on us. They can really do experiments very easily. This is already done all the time with A/B testing to test a particular feature. So these are clearly application areas that could prove to work. For me, they're also a bit scary, and that is also why I really focus my research on an application to science as much as possible.
Okay, so moving to the next question, Diego asks, I am wondering how we can apply your work in my field of research, which is capital regulation of banks, including a Brown penalizing factor.
Okay, Diego, unfortunately, I do not know what a Brown penalizing factor is. And also, I mean, I know what capital is and what banks are, but what capital regulation of banks is, I have actually no idea. If you can write in the bottom, maybe we can answer it later.
Okay, so I don't know if it's a follow-up question, but Diego has another one that says, because I find it interesting if it can explain other variables that are not taken into consideration initially. So maybe Diego, if you can be more specific, we can go back to it. In the meantime, there's another one from Carlos that says, what would you say is the current state of the field of causality, and what are your hopes for the future of it?
All right. Well, I guess I will share my personal scientific opinion here. Don't quote me on it. I think, so first of all, the field is not very old. It's perhaps 30 years old. And I think there was a huge progress at the beginning when it comes to thinking about causality, to formalizing it, to really justifying it as a field, because at the beginning there was a lot of skepticism from people in statistics. I think in my particular subfield, which is causal discovery, so given data, recovering causal structure, I think most of the field still relies on these algorithms or these ideas of using conditional independence and dependencies that we've measured in the data. And so observational data still has a lot of importance. But in my personal opinion is that these approaches, we already know they don't work well. But the issue is that it's very difficult to come up with other ways of doing causality. I think besides causal invariance. So basically other ways to think about what kind of traces causality leaves in the data. And beyond causal invariance, there's maybe another few approaches, like, for example, information geometric causal inference. But they're still very much very exotic research topics. My hope for the future is that we come up with other ways to think about causality. This is particularly the kind of stuff I'm working on. Whether it works or not is a different question. But I think also the approach that we have to take is that there is no one silver bullet for everything. Causality will look different in different systems that we study. And what is important is actually to for example, axiomatize causality. So same as before, we said, okay, we assume that there are no cycles, which doesn't apply to all systems. It might apply to some. And I think it's okay to make these kind of axiomatic statements about causality, but then we have to be very careful in transmitting them to the people who actually use these methods, to the practitioners. And what I would hope is also that there's more communication between the people like us who develop methodology and the people who actually use our methods. And also that maybe the methods that we design are also able to say when some of the assumptions that they rely on are violated. I mean, this is already the case for example, very basic linear regression. Applied statisticians already know how to quickly check whether the assumptions that they're relying on work or not. So I think, yeah, basically my hopes would be what I said, that we're able to recover causal structure in a way that is reliable, but also transparent enough for people to trust and make decisions with it.
So before reading the next question, actually, if any of you, Carlos, Paula, or Ines, if you have any questions, feel free to ask after this one. So from Claudio, who says, which could be the ethical implications of using AI causality in the future? How can we avoid the fake news kind of way to discriminate what can be a possibility of real causality from another false outcome?
I feel this question is a bit flies a bit over my head. I know there's a lot of research on fake news and how they propagate and all of that, and I'm by no means an expert. I think actually the biggest contribution that causality can do for fake news is not even at the algorithmic level, is keeping always in mind this thing I said before, that correlation does not imply causation. And we have this sort of bias as humans. We do it all the time. We see two things happen together and we immediately assume a causal link. Actually, we see this in headlines all the time. So for example, I think there was this example on John Oliver where there was this tweet being propagated where they had a map of the US of where 5G antennas were being deployed, and the same map below with the cases of COVID. And they were clearly correlated. Where there were a lot of 5G antennas, there was a lot of COVID cases. And so people jumped to the conclusion, oh, look, 5G causes COVID. But there's these two variables are clearly correlated, but there is another explanation, which is simply that 5G antennas are deployed in places where there's a high population density, which is also where COVID spreads. So these these are very simple, let's say, causal reminders, but always remember that, that correlation does not imply causation. I think more than what my field can contribute, I think statistics and these kind of basic statistical statements to understand the difference between correlation and causation and understand basic statistical statements that are made in the news, I think this should be a part of the curriculum that everyone studies in high school, for example. But that's just my grain of salt, of course.
Now there's a question from Anina saying, I guess causality perhaps in the future will be able to get physical laws without knowing physics. But do you think there is a merit in incorporating, for example, the laws of thermodynamics into your causal structure?
So hi, Anina. Thanks a lot for the question. It's a really good question, actually. Well, whether we will be able to get the physical laws without knowing physics is, I'd rather not express my opinion there. Maybe, maybe not. I think a problem that we have in causality, for example, is that the relationships that physical laws follow are quite mathematically complex. And that is something that is still quite difficult for us. So learning these kind of important representations from the data and then learning causal relationships on top. But I think this thing you say of including the laws of thermodynamics is actually very, very interesting. There is a subfield I'm particularly interested in biology, which is called basically metabolic network reconstruction. So how we map the metabolism of a bacteria. And what is very interesting there is that you can limit already the sort of models that are possible by incorporating this kind of background knowledge. So thermodynamics and basically how, if you have a certain belief of how the system might behave, and there's only a limited ways of how the system might behave, I think it's for sure very useful to incorporate into your learning algorithm. So yeah, that's a good question.
Okay, so I think that concludes the questions so far. So if any of you have any questions, either for Carlos, who's still here, or Juan, feel free.
I have a question for Juan. I mean, first, great talk. I think this is, as I said before, the real thing. I mean, and we should focus our efforts on this. It's also a super difficult problem, right? As you acknowledge. A question I have, okay, I guess I have a couple of questions. One is more kind of open-ended, like, let's say you could enhance an agent, right? An agent that can make decisions and interact with the environment to some extent, right? With an approximate or the correct kind of causal diagram as the one you have over there. Mm-hmm. I guess my question is how much you can leverage such causal relationships, right? I mean, I would imagine a lot, but and maybe if instead of knowing the right causal graph, if you have like some approximation that comes from experts, like human experts, right? Mm-hmm. How quickly you think the ability to do partial experiments, like, I don't know, if you are driving a car, you have some freedom, right? You can turn left or right, but you cannot maybe cross a wall, right? Because it doesn't work, right? But how fast do you think you can translate that freedom to interact into first, like, refinement of your causal graph, and second, on making better decisions, right? I mean, I guess it's quite open-ended, but
okay, so in terms of how quickly you might disprove a causal model, I would say, of course, it depends on the particular causal model and the kind of experiments that you can do, how strong these interventions can be. Maybe driving a car, you can turn the steering wheel a little bit, but you cannot just turn it completely to see what happens, right? Mm-hmm. I think what is nice is that there's already quite a lot of work done when you only know parts of this causal model, because as we saw before, there's only a limit to what you can learn from observational data. So there's, for example, a lot of work in, once you've reached the limit of what you can learn from observational data, deciding on optimal experiments to quickly learn the rest of the things, right? I think that's an approach in terms of how fast. Well, it depends on what you mean by fast, and I think, of course, it would mean by the particular model, right? Mm-hmm. There was another part to your question, I think I'm forgetting.
Like how much I mean, I guess the answer is probably depends, right? In both cases. The second part of that question was how much you can improve your decision making by knowing not only correlation between variables, but causation, right?
Well, of course, this depends what kind of decisions you're talking about. So if you're an insurance company and your goal is to, insure people at a price that allows you to make a profit at the end of the year, you don't really care about causality, right? You just care about making a prediction that on average holds and makes you money. If the decisions that you're talking about are decisions that mean interacting with the world around you or with a particular system, I think causality, there's no way to avoid it. Because what you would like to know is, okay, if I want to change this variable, which other variables can I manipulate, right? And I think it's also a layered problem, because once you have the causal structure, even if you have not fully characterized the relationships between these variables, even if you have not modeled it, then that already gives you a place to start looking. And so you might start doing experiments in this area to fully map out the relationships, particularly when these relationships are so complex that you might need something like a Gaussian process or a neural network, right? So I think when your decisions are about manipulating something and knowing what to expect, causality is, you cannot go around it, basically.
And related to that last part, I think I have a second question related to the sensitivity of the statistical methods, right? So if you think of a complex system, right? For example, let's say your variables are images. So every X here in the plot is 1 pixel. You have thousands of them, right? And if you put on top like a modern model that takes that and learns some useful representations that are extremely correlated, right? What you discussed during the talk, I mean, you may have a very accurate statistical model that always says missing cause, right? Because there's actually a missing cause, right? But then it's not very useful, right? So how do you adjust like the sensitivity to be useful, but still truthful to some extent?
Yeah, of course, this is depends on how you penalize, for example, false positives and false negatives, right? So, for example, if you don't care about having a lot of causes which are not actually there, then maybe it's okay to go in a certain direction. But for example, if it's the other way around, then you say, okay, for example, what causal invariance does is it takes the other approach. So causal invariance is then implemented into a method called invariant causal prediction. And the advantage of invariant causal prediction is that if it tells you something is a cause, it's sure with high probability. So there, for example, you prioritize the opposite thing. You say, hey, actually, if you can't learn anything, then don't tell me anything. But there are methods which go the other way around. So this, I think, is also up to the practitioner. But being able to do these kind of things depends crucially on the underlying principle that you're using to infer causality, I think. At least in the experience I've had.
I see.
Okay, so if there are no last questions for either Carlos or Juan, we can go ahead and wrap up the event. So no more last questions for either of them. If not, that should be a wrap up. So we can go ahead and thank you everyone for attending today. Thank you especially to Carlos and Juan for talking and presenting. It was for sure helpful. So yeah, thank you everyone. And
thanks a lot to you and the invitation.
Thank you guys.
Yeah, thank you.
Yeah.